So hello guys, as Ross mentioned, it works. I decided to just start with a brief CV so you know who you're dealing with today. So I got a master's degree in the Netherlands, lovely University of Delft, then went to the US, did a postdoc there in an even lovelier Rochester, postdoc at the University of Toronto, and then came here. I'm now here a professor in physics. Ross mentioned this already. I have research interests that revolve around wave propagation, nonlinear optics, solitons, fiber optics, periodic media, waves in random media. I'm associate director in QDOS, and Ross's somewhat elliptical comment referred to the fact that in my spare time I'm the editor-in-chief of Optics Express, one of the main optics journals. So going back then to the outline, here are some of the textbooks, the standard textbooks in this area for which I've drawn some of the material. And what I'm going to cover in these two lectures is, if I can find myself a stick. I'll start with discussing nonlinear optical media. There's saying that something is nonlinear. It's not a particularly good descriptor. It's equivalent to saying that the wall here is not blue. It doesn't tell you what it is. It simply tells you what it not is. So there's a number of different classes of nonlinear materials. Yes. Okay. Good. So this is a red one, guys. Just pay attention. I have other ones with me. So I'll talk about a particular class of nonlinear materials called the quadratic ones, and I'll give you a bit of a hint as how you do calculations in those materials. Now, there I'll stop. This is more or less the general theory. And the reason I'm stopping there is A, I've got to run out of time, and B, some of my colleagues will be discussing some of the nonlinear optics experiments that are carried out here and at the university, ANU, the Australian National University in Canberra. And this is some introduction to some of the concepts. I'd love to talk to you about those experiments as well, but I regret that I have to share these, lectures with my colleagues. All right. So let me start by telling you what nonlinear optics is, or some of the characteristics. So we are used to thinking of optical materials, and we'll be mostly dealing with transparent materials. All right. And so we're used to thinking about the properties of these materials as a refractive index. And if there's a bit of absorption, there's an absorption coefficient, and those two may depend on frequency, and in fact, in general, they do. Okay. Now, the nonlinear optics is the field where these parameters start to become properties that depend on intensity. And indeed, it is true that the refractive index of this glass here, as you know, is about 1.5. And we turn the light off, the refractive index of that material is slightly lower. It's probably differs by 1 part in 10 to the 10th, if not less, but there's a very small refractive index change between when it's light and when it's dark. Now, these effects are pretty weak, as I just mentioned, but one of the aims you have in nonlinear optics is to find geometries where these intrinsically weak effects somehow become strong. And not so much my lectures, but some of the lectures that you will get in the coming days will tell you the tricks that people play to make these intrinsically weak effects appear strong. Okay, one of the signatures, and I'll get back to this later again, one of the signatures of a nonlinearity is the emission of new frequencies. So let's contrast that with a linear system. And I'm a physicist, so I think naturally in mass spring systems. The electrical engineers amongst you may think in terms of LRC networks, right? And that is your canonical second order system. It's, unless you hit it too hard, it's linear, And one of the characteristics there is that linear systems are really dumb. And that is they can't make up new frequencies. If you drive it at a particular frequency, like 10 hertz, I'm thinking of mass spring here, drive it at 10 hertz, well damn it, it's going to oscillate at 10 hertz. Okay? It can't do, and what it could do, if you're on resonance, it oscillates at 10 hertz readily. If you're way off resonance, it will do so against its better judgment, but it will still do it. And what that means in practice is that the amplitude is going to be very small. Okay? But if you drive it at a certain frequency, a linear system will always respond at that frequency. So the characteristic then of these nonlinear systems is that they have brains and that they make up their own frequencies. There's a number of different classes of materials, of nonlinearities I should say, by which the frequencies that are generated depend on the type of process you're looking at. This is an example of a process I won't talk about here, but just as a bit of a teaser. So this is a plot that gives you intensity versus wavelength, and this is the pulse going into a fiber of some description, right? And it has a very narrow wavelength range. And now you let it propagate through 100 meters of fiber at a pretty chunky peak power of 235 watts. Right, that's big, that's a lot of energy, high energy density. And you see that the spectrum at the output has been broadened by about a factor 10 or 20 or so. Okay? Clearly new frequencies have been generated. It could never be done with a linear system. Okay? And this is the type of nonlinearity I won't be talking about. I will be talking about other nonlinearities whereby you generate other types of new frequencies. Now, nonlinear optics, I should also say, is a fairly, I guess, the field was born with the laser. As I mentioned earlier, these nonlinear effects tend to be weak, and therefore you need, in general, very high light intensities to make them clear. Look at this 235 watt of laser light. That's, as I mentioned, a lot of oomph. That's a technical term you understand. And so you couldn't really do nonlinear optics until the laser was invented, but once it was, a whole bunch of new effects were discovered in the lab and described theoretically. And the reason we're interested in here, and this is an application that I won't really get into, is for optical processing. Since the material is nonlinear, you generate new frequencies, you can get light to interact with itself or with other lights, and then of course you can make use of. All right, I mentioned just a minute ago that nonlinear optics is a 50-year-old area. You may think that it's a pretty sedate one. It's slowing down, it's settling. Nothing could be further from the truth. There's a lot of current interest in nonlinear optics in a lot of different areas, hot topics. This is a fairly random cross-section. One of them, for example, is optical supercontinuum generation, which is a process by which you put a short pulse in an optical fiber, and what comes out has a spectrum that is as wide, so wide that the light looks white. And so you'll have white light with the intensity of a laser beam, which hasn't been possible until fairly recently. There's a lot of interest in nonlinear optics for quantum information. It turns out that these newly generated photons can have, if you play your cards well, interesting quantum properties, and we may, if we have time, have a look at that. Frequency cones and optical clocks. I guess that will take me a little while. I guess the other one is perhaps an interesting one is slow light for enhanced light matter interactions. There are processes by which the speed of a pulse in a material can be made very, very small, so the light that propagates very slowly. That, of course, is neat in its own right. We are, I guess, physicists and electrical engineers, and we like neat things, and the idea of having light travel very slowly is appealing. In addition to that, you can understand that if light propagates slowly, you could have the situation that it interacts that it interacts more strongly with its environment than it otherwise would, okay? Because it hangs around more often. And for that reason, these nonlinear effects, which I mentioned earlier, are pathetically weak in general, are also enhanced. And in fact, you can show that for a number of these slow light schemes, the nonlinear interaction becomes quadratically larger if the group velocity of the light goes down. So if you slow your light down by a factor 10, the effects become 100 times stronger. And that is one of the things that people are trying to make use of in some of the state-of-the-art experiments. Okay, I won't go through all of these in detail, but it just gives you an idea. Now, this is clearly a ship or a river, and the only reason this slide is here is not because it's associated with nonlinear optics, but I just wanted to mention that there's a lot of nonlinear physics or nonlinear dynamics around in nature. Optics is a very neat, clean environment to do experiments, but it is by no means the only one. And one of the other famous ones are water waves, which are extremely nonlinear, particularly when the water is not particularly deep and the waves feel that there is a bottom somewhere. Okay? And the idea of the soliton, which will be discussed in detail in some of the subsequent lectures, actually originates from water waves and with barges going through shallow canals in Britain. Okay? So here optics is in fluid dynamics. Then there are some other areas where this nonlinear effect becomes important, and those are so-called rogue waves. Rogue waves have been known, or have been, I guess, suspected in ocean waves for many years. There have always been reports of ships coming to a sad end, not often not understood, and what is now kind of starting to be realized that due to the non-interaction between water waves, by sheer fluke every now and then, you generate very strong waves that are an order of magnitude possibly larger than typical waves. And this is an example of such an event. This gives you height in meters of water waves versus time. And you suddenly see out of nowhere coming this really big one. And if your ship is there, then you're in serious trouble, of course. All right, and this is some examples of ships that have done that. There's now satellite investigation of this, or observation, I should say. These rogue waves, as they're called, are found on the various oceans that are on Earth, but usually there's not a ship around. And if your ship is around, then of course you're in trouble. The reason I'm bringing this up is that the ocean is a pretty rough environment, and you don't have much control over it. Experiments like this can be carried out in optical fibers, and so this is an area where optics can pay back its debt to fluid dynamics. Okay? I should also say that by no means is this exhaustive. I don't know if you know about plasma physics, but just about anything in a plasma is nonlinear as well. And so there's a lot of concepts in nonlinear optics that have counterparts in plasma physics. Okay, now this is something that I already discussed more or less. Let me just go through it to make sure I covered everything. Characteristics of a linear medium. It's characterized by a refractive index and an absorption coefficient independent of the light intensity. If you're in first year, well, the refractive index of glass is 1.47, and that's about the end. There's no new frequencies generated, and superposition holds. Namely, if you put two light waves through, they don't know each other's existence. They're too dumb to notice the other. Okay? In nonlinear optics, in contrast, it's all the other way around. The refractive index and often also the absorption in general depend on the light intensity. Frequency of light changes. I had that example of this broadening, spectral broadening of this pulse as it passes through the medium. Superposition is violated, of course, in anything that's nonlinear. And because that is true, because superposition is violated, one beam would notice somehow that another light beam is there. And by that interaction, you can play all kinds of tricks. For example, what often happens is that the phase of one light beam is affected by the presence or absence of another light beam. And if you put that in an interferometer, then you can imagine that you can do some things, which indeed people are doing. All right, now, before getting into the mathematical description of nonlinear optics, what I wanted to do is just take you through some of the, almost tempted to say to take you through memory lane, but just to remind you of what is behind the optical properties of materials. How are they defined? What is the physics? Where do they come from? Okay? And the kind of the simplest, non-trivial description of an optical material is that it consists of atoms, and then each atom is modeled as a harmonic oscillator. That seems ridiculously simple because atoms are clearly more complicated than that. But in fact, many of the properties of optical materials can be understood in this way. So it's actually not too bad. Okay? And the idea then is the following. This is a classical description, so the electric field is described, the light is described by an oscillating electric field. All right? And so imagine you have an atom with a nucleus positively charged in this nebulous cloud of electrons negatively charged around it, and now you will put a field over it. And the field, in the wisdom of the person who made this figure, points to the left. Okay? Then remember from electrostatics that the force on a charge is Q times E. It depends on the sign of the charge, right? So if the field points to the left, yes, then the positively charged nucleus is pulled to the left, and the electrons are pulled to the right. And what this is, of course, is a dipole, because they have equal and opposite charges, but the center of the positive and the center of the negative charge are slightly displaced from each other. So when light is incident on an atom or a medium, which is a collection of atoms, it creates all these dipoles. Okay. And just a definition here, the polarisation is the dipole moment per unit volume. I have some equations on the next slide. All right, so this is then the mental picture here. We have this light wave here, and the light wave pulls the positively charged nucleus away from the negatively charged electrons, forming these localized dipoles. Okay, now what can we say about that? Well, let's put this in a little bit of math in. Most of this is definition. There's one key assumption. So the first one you may remember is that the dipole moment is defined to be the charge, minus E, or E, the sign doesn't really matter, multiplied by the distance between the positive and negative charges, okay? Now the negative charges are distributed, but you can imagine there's some kind of average position, right, center of charge. So you set up a dipole moment, and that is E times the charge times X, okay? Now, then the key assumption that leads to linear optics is that you need a relation between his dipole moment, or alternatively, of course, this distance, and the applied and the field that this atom sees. Okay? Now, the simplest thing is to say, well, I have this electron and this nucleus, and they're together. Now I apply a field, and they're just pulled away from each other a little bit. If I double my fields, then I could imagine or could assume that I pull them twice as far apart. Okay? That is the lowest order approximation that you can make there, and under that assumption, this distance is proportional to the electric field, and there's some coefficient there, which is called the polarizability. And then it is an atomic property that you can look up, or you can calculate from, if you know the wave function, you can calculate it. Okay? So this is the big one. The rest is kind of bookkeeping. So the next one is to say, well, we define the polarization P to be the density of these dipoles multiplied by the dipole moment per atom. Okay, so P is then something like the dipole moment per unit volume. This is standard stuff that you've done in electromagnetism sometime. Stuff like this is sometimes a bit of a suppressed memory, which is why I go through it in some detail. Okay, and then from this it then follows that the relation between this macroscopic property of P and the applied fields is also a linear one. There's an epsilon naught that makes up the numbers. I'll be using the SI system of units here, so you have to carry this nasty epsilon naught around. But then the real business end is this parameter chi, which is called the susceptibility. Okay, now the relation between alpha and chi is not so obvious, because if you have lots of atoms together in a small volume, they interact with each other. All these dipoles affect each other, and therefore, in order to go from alpha to chi, it's not just multiplying by density. There's some correction factors there, but let's not worry about it. Oops, I'm just losing my badge. All right. So this linear assumption here gives you this linear relation between the applied field and this response of the medium, which is this microscopic version of the dipole moment. Now, then to just follow this particular yellow brick road, this is the expression from the previous page. I just remind you, this is an example of a constitutive relation. It tells you what kind of stuff you have. And then you may remember that often in electromagnetism you define this field D, the displacement field, which is essentially the sum of the applied field and this response of the medium P, and that defines your dielectric constant epsilon r, which is 1 plus chi. And then finally the refractive index, the thing that we're really interested in optics, is the square root of epsilon r, and it's the square root of 1 plus chi. So when you trace this root back, you can see that the refractive index of a material is ultimately linked to the ease, well, apart from the density, it is related to the ease by which you can pull the electrons away from the nuclei. Okay? It's a harmonic oscillator. You can imagine there's kind of a spring connecting the positive and the negative charges, and so this the refractive index via this somewhat roundabout way is a measure for the spring constant of that spring. Okay, plus a density thing. All right. Now, in general, chi is a complex parameter, and since chi is complex, and again you kind of follow this through the formalism, you find that that epsilon r is complex, and therefore n is complex as well. The real part of n is related to the refractive index. The imaginary part is associated with the absorption. Okay, and I'll mostly ignore absorption because it's a bit of a nuisance, and you can usually avoid it if you wish. All right, so this was the linear optics. Let's see how things change when you go to nonlinear optics. And again, let me argue what is going to happen before I take you through this. So remember, the mental picture in linear physics is that you have this nucleus, and you have this cloud of electrons, and you pull them. You have this field that pulls them in opposite directions, and to lowest order, when you double the field, this kind of separation doubles as well. Now you can imagine that if you start pulling really, really hard, the electron cloud starts to run into the neighboring atom. Right? Clearly, once that starts to happen, this whole linear relationship goes out the window. There's a couple of other things that happen beforehand. If you pull the electrons away from the nucleus too far, you find that this electron shell structure starts to distort, clearly, because it was designed to have the nucleus in its center, and it is no longer. All right? So this electron shell is going to distort. And the consequence of that is that this linear relationship that we were talking about earlier falls by the window. There are going to be correction terms. And those correction terms are provided your field is not too strong, are fairly small. Clearly, if your applied field is so large that it is comparable to the fields that holds the atom together, namely the field that you get between the nucleus and the electrons, then you ionize your atom and all bets are off. And you're in a completely different regime, and nonlinear optics is not about that regime. There is other branches of physics which are very interesting, but that's not what we're doing here. So here we're in that regime before ionization, where this linear relationship starts to fail in a subtle way. And that is a regime that you can reach with modest lasers. Right? To ionize something with a laser, you need a very large one. This you can do with fairly inexpensive lasers, and therefore in a sense the experiments are more accessible. Okay? And I guess the picture that goes with this is that this straight dashed line here is the linear relation between P and E. If the oscillations become too large, or sorry, if the applied electric field is too large, then you get small deviations from that. And in this particular case, you get a little bit of curvature. Okay? And it's these effects that we will be interested here. This, as an aside, is the same thing that happens in a mass spring system. If you pull a string too hard, it starts to behave non-linearly. Clearly, if you have an LRC network, you get the same thing if your voltage becomes too large. So one of the components starts to behave non-linearly, and you get this non-harmonic behavior. All right. Now, how do we describe this mathematically then? And let me just go back to that figure. Okay? You say, well, it is to a good approximation, this is linear, but there's a bit of correction stuff there. So if you want to describe this mathematically, this is crying out for something like a Taylor expansion. Okay? And so a standard way of describing nonlinear properties of nonlinear optical materials is by this Taylor expansion type formalism that was developed by Bloomberg, who received the Nobel Prize for his work in nonlinear optics in the 1970s. No, around 1980. He is still going strong, and he still pops up at conferences here and there. All right, so this is the relation that we had earlier. It is then kind of understandable that if you want to generalize this and include small deviations from this, you write it in essentially as a power series. Now, it's a funny power series because the things you deal with are not scalars, but they're vectors, which is why I don't write this as E squared, right? Because the square of a vector doesn't really exist, and this is an E cubed, and for this reason, all these guys here are tensors, and that is messy stuff that we don't really want to get into here. I could easily spend 10 lectures on that, and you will all be bored out of your skull. So would I be, by the way. So let's not go there. I'm just flagging that these things are tensors in general. This guy 3 is a fourth rank tensor. It has 81 elements, all of which depend on frequency, some of which are related to each other by the properties of the crystal, but in general it's missing. But again, let's ignore that. This guy, as I mentioned earlier, is called the susceptibility, and then by analogy, these are called the nonlinear susceptibilities. And this term here represents the linear part of the polarization, and these two here represent then obviously the nonlinear part of the polarization. Okay? And as I mentioned, the fact that you deal with vectors makes this messy without necessarily making it particularly interesting, but you just have to suck it in and deal with it. All right. So this is this series of Bloomberg again. Oh, I should just mention before going on that the first nonlinear optical experiment was done in was done within a year of the invention of the laser. The Bloombergian work is a little bit after that, it's 5-10 years after that. And so a lot of theory was developed before the Bloombergian work, okay? And all using different notations. And so this field is a bit of a dog's breakfast in that sense. That different books have different definition because the theory was developed at a number of different places. And this lovely Bloombergian theory, which is kind of an umbrella covering everything, was developed in a sense 5 years too late. And we will see that the standard theory of nonlinear of this second order quadratic term here doesn't use the chi2 in general, but use another symbol. Okay, but I've started out at least in this unified way. Okay, now chi1, which is in essence the refractive index with some bells and whistles, as we showed earlier, is of course always non-zero, unless you have some kind of freak property at a particular frequency, but in general it's non-zero, unless you do a vacuum. Chi2 is different. Chi2, for reasons that I won't go into here in detail, but if you have a material with inversion symmetry, and what that means I'll tell you in a minute, then this parameter chi2 is identically zero by symmetry. And in that case, the lowest nonlinear term you have is chi3. Now, what does it mean to have inversion symmetry? What that means is that you have your atomic arrangement, you replace x by minus x, y by minus y, z by minus z. You do that while you close your eyes, then you open your eyes again, and if what comes out is identical to what you started with, then the material has inversion symmetry. If you see something else, it doesn't have inversion symmetry. Okay? So, an example is silicon. It has inversion symmetry. This is the diamond silicon has what is called a diamond lattice. This is a diamond lattice. Ignore the difference in the colors of the balls. Each of these balls represents a silicon atom, and you may remember that the bonding is such that it has 4 nearest neighbors, and you can see it here. If you apply this inversion algorithm to this crystal, again ignoring the color of the balls, then every atom ends up on a position where there was an atom before. And so again, by definition, it has inversion symmetry, and therefore chi2 is 0, and therefore the lowest nonlinear term is this chi3. In contrast, gallium arsenide, also a semiconductor of course, but then this is its crystal structure. The black ones would be, say, gallium, the white ones would be, say, arsenic atoms. If you now start this algorithm by which you replace x by minus x, y by minus y, and z by minus z, you find that where you used to have a gallium, you now have an arsenic atom, and vice versa. And therefore, you do notice the difference, and indeed gallium arsenide does not have inversion symmetry, and therefore indeed it has a non-zero chi2. Now, for reasons that we will come to towards the end, gallium arsenide is not particularly good for nonlinear optics, or at least quadratic nonlinear optics associated with this term, but we will have a little way to go there. Now, an interesting one, of course, is glass. It's got, of course, your premier optical material. It clearly has no inversion symmetry because it is amorphous. The structure of glass internally is that you have these rings of silicon atoms with the oxygens kind of floating around there, and these are 5 or 6 or sometimes 7-membered rings. The number of atoms in the ring is arbitrary, right? And so there's no way that if you flip everything around, you get exactly back where you started with. So, however, what is important is not so much the inversion symmetry on an atomic level, but the inversion symmetry when you average over a wavelength. If you average over a cubic wavelength, then if you imply this inversion algorithm, you get more or less the same feedback. And therefore, for glass, the standard variety glass, this chi2 is indeed 0, and so optical fibers, all the nonlinear experiments are with this cubic nonlinearity here. And as I mentioned earlier, these coefficients all depend on frequency and do so very rapidly when you're near a resonance. We will not go into this. This is again something that is a couple of lectures in somewhere. Okay, so this is then the general relation. There are people worrying about chi4 and chi5s, but my personal opinion is that life is fairly short, and certainly too short to deal with chi4 and 5, but there are colleagues of mine who don't agree with that. So what I will do in this set of lectures is essentially deal with chi2 and see what kind of effects come out of this chi2. There are more additional and in many senses more interesting ones coming out of that, but some of my colleagues will be talking about that. Okay, so here is where I warned you earlier that everybody has their own definition. This is what you often find in literature. Rather than a chi here, you have a d, and for reasons that is not clear, there's a factor 2 there. It's let's not go where that comes from. Okay, so instead of the chi2, we deal with this d parameter. This d is also a funny tensor, depends on frequency, and there's a number of optical effects that come out of this that are mentioned here, and I will mention them later on. And as I mentioned, only without inversion symmetry. Now, these materials, for reasons that I already mentioned, namely, they need to lack inversion symmetry. Most materials, in fact, do not have a chi2 or a d. Okay, so you find that the materials that are used in this quadratic nonlinear optics are really weird ones. Okay, there's ADP, which is ammonium dihydrogen phosphate. I think it's pretty obscure apart from the fact that it's used in nonlinear optics. And this is the, this should be a little bit here on I'm sorry, it's this PowerPoint makes it automatically in capital when you start with it. Thought I picked them out, but I clearly didn't pick them out. Pick all of them out. Okay, so these are, I mean, this is not exhaustive. I don't want you to know this, except that these are weird materials, and that the units of this chi2 are picometers per volt. It's an inverse voltage, which is volt per meters, and they're so small that it's not meters per volt, but picometers per volt. That makes the numbers a bit bigger. Notice that gallium arsenide has this whoppingly large nonlinearity, but for reasons that we will discuss later, you can't really use it, regrettably. Notice also that this chi2 or d parameter can be positive or negative, and that it depends, as I mentioned earlier, these guys are tensors. They have lots of different tensor elements. So when I put a range here, this is the range of elements that the range of sizes of these elements. So it varies between 2 and 18, depending on the orientation and the relative direction of all the electric fields. Okay, so let's see what I've now mentioned earlier, that linear optics is kind of boring because it doesn't have a brain. Everything that you put in comes out in some way. Let's see how nonlinear optics is different. Okay, so let's look at the simplest conceivable case. We have some fields with frequency omega. I'm ignoring the position dependence. I will get to that later. That will become important later, but let's not worry about that now. Okay, so I have a sinusoidal of varying fields, and I put this in a nonlinear medium, the response of which is given by this nonlinear polarization. Okay, and remember it's proportional to e squared. I'm ignoring vector effects here. We're among friends now. Okay, so I'm ignoring all this vector stuff. And remember there was a 2d instead of chi2. Let's not worry about that either. The business end is this e squared. And if I take the square of this, well, cosine squared, right? Cos squared omega t is a half plus a half to omega t, right? And that's what you see here. You have this half here. There should be a 4 down the bottom. I forgot about that. And then you have your 2 omega t. Okay? So one of the things you see here immediately is that if I drive this at frequency omega, then this nonlinear polarization is going to oscillate at 2 omega. And remember, as I mentioned earlier, the hallmark of nonlinear optics is that the material generates its own frequencies. And this is the simplest example. Right? This is not this broadening that you saw earlier, which is a kind of 3 effect, but this is frequency doubling. Okay? You get something also, you have these dipoles oscillating at 2 length. And we will get back to that later. There's also the DC term, it's called optical rectification. It's one of these effects that is always in textbooks, but it's really dull and not particularly useful. So let me ignore it here. Okay? Let's forget those bullets. Okay, now, for a little bit of light relief, you say, well, that's all pretty academic, this frequency doubling. Now, it turns out that your laser pointer is a good has a frequency double in it. This is and thank you for this nice prop. So this is a red laser pointer. And it turns out, I won't shine into your eye, the red light is away from the peak of our eye curve. We can't see red light very well, which is why this looks pretty dim. Okay? We can all see it, but it's not particularly bright. This is essentially the same thing, except that there is one of these nonlinear crystals sits in here, and we'll get to some of the details in the second lecture, that doubles the frequency. Now, I'm lying somewhat. The fundamental frequency here is not red as it is here, but it is infrared. One of the most efficient lasers that exists is a YAG laser, and it emits at 1.06 microns. So that's in the near infrared, but we can't see it. If you frequency double that, you get to 1.06, the wavelength halves. So the wavelength becomes 0.53 microns, and that is green. And that is really near the peak of our visibility curve. Our eyes are very good at picking up green. Right? This one will blow your eyes out, so you have to be careful. But in part it looks brighter because our eyes really pick up green light much better than they pick up red light. Just as an aside, what I'm doing here is highly illegal because some people started to shine these bright lasers like this at airplanes, at the cockpit of airplanes from the ground. And there was a great panic. And so these laser pointers are now forbidden goods. You can import them only if you have a formal permission from the government. And the permission can be obtained from the same people that give you permission to have firearms. So this is very serious stuff. Anyway, so don't tell them because I'll be in trouble. All right. So this frequency doubling actually works, and this green, as I mentioned, comes out of the infrared. All right. So this is just a pictorial kind of interpretation of this. This is the field. This curve here, and if you have a linear medium, well, it responds linearly. You get a sine with a different amplitude. As I mentioned earlier, you drive it at 10 hertz. Well, it's going to oscillate at 10 hertz because it can't do anything else. If I have a nonlinear material, so my optical field is stronger, then I get these deviations in my from the pure sinusoidal response. You can do a Fourier analysis of this, and you find that this nonlinear response is the sum of a DC offset, which is this optical rectification that I mentioned a little bit earlier, plus the linear response here, the dominant one, plus this small nonlinear response. And if you add them all up, you get this guy here. And it is the effect associated with this small second order response that we're seeing, and that gives rise to this green light that I just showed. And this is probably a nice place to have, nice time to have a short break. So we'll break and I'll see you guys in 10 minutes.